Hello, everyone, and welcome to our capstone presentation. We are Team FaultLine, and our sponsoring company is Acumentrics. Our team consists of 2 computer engineers, Dan Foreman, and myself, Brianna MacDonald, alongside 3 electrical engineers, Don Barata, Lucas Alcides, and 80s Embla Ludvigsdottir. Before we get started with our project, first, a little bit about our sponsoring company. Acumentrics is a company based in Walpole, Massachusetts, and they are the trusted market leader in delivering RUPS devices, which stands for Rugged AC/DC Uninterruptible Power Supplies. They are also the top supplier of US-made power electronics for defense contractors. Currently on the market, they have the RUPS device, as I described previously, as well as portable power pack units known as Pack Power. Additionally, currently in development is a past capstone project called the Smart PDU. With over 25 years of experience, Acumentrics is combining their knowledge in collaboration with our project.
Our project motivation revolves around the idea of predictive maintenance. Predictive maintenance is being able to detect equipment failure before it occurs in order to prevent this. Acumentrics currently doesn't have a way to maintain their equipment until it's already broken and back at their company. Due to this, we want to implement this into their systems. By looking at this process here, you can see predictive maintenance usually follows a structure of monitoring some data or some information and inputting it to machine learning. From here, it is then output into a fault prediction. Predictive maintenance usually involves the use of sensors, where in Acumentrics equipment, this isn't effectively deployable, and therefore we need to seek an alternative. Due to this, we are going to use power signature analysis. All devices produce some type of distinct electrical characteristics. And from here, we can derive things such as the active and reactive power. Using the power triangle, we can then calculate the power factor. Additionally, we can achieve a higher level of distinction between devices by using the harmonics. By taking this then information, we can then produce a machine learning model, or input it into a machine learning model. From here, we have an example diagram where an algorithm is attempting to classify cars. We have some test input data, where it's then input to the model, and then is output as either a car or not a car classification. Machine learning bridges the gap between input and output, where in our project, we're trying to bridge the gap between power signature analysis and that of a fault prediction. Machine learning algorithms typically take a large amount of data, and in the same analogy here, you can think of that as to produce an accurate result, we need to think about all the different types of cars. There's Jeeps, there's Teslas, there's Toyotas. For this, the model would need to train rigorously. Taking this analyzed power data and this machine learning algorithm output, we can then achieve a fault prediction. Here, you can see that we want to be able to determine if the device is faulty or functional. In our case, we chose a fan. This is due to its gradual electromechanical failures that can be induced to the interior components. This affects the power consumption of the device and the motor power signature, and because of this, we want to prevent catastrophic failure within the equipment. Tying together these concepts of power signature analysis, machine learning, and fault prediction, we can then realize our anticipated best outcome, which is a functional prototype capable of modeling and detecting abnormalities in behavior. Additionally, we want this prototype to include features such as modeling a single connected device and being non-intrusive or non-invasive to the interior components. And additionally, this would have to rely on the power signature of the device. In order to realize this anticipated best outcome, we have worked on 3 major tasks.
So the 3 major tasks are collecting data, teaching the model, and making predictions. The electrical engineers on the team have been working on a device to collect the data. And the first step in that was to select an IC. The IC that we selected was the ADE7880 chip from Analog Devices because of its high accuracy and ability to perform harmonic analysis. The chip is made for a polyphase application, but we want to use it for a single-phase application, and there our design skills come in handy. For time efficiency, we decided to get an evaluation board that had a microcontroller to take care of the communication piece. Next step was to configure the evaluation board. We simply wanted to plug in the fan and get measurements of both the current and the voltage. So here you can see the actual evaluation board that we have been working with. Next step was to calibrate the board to get accurate measurements. To calibrate it, we had to use a programmable load to feed in known values. to correct phase delay, gain, and offset. To visualize the data, we have been using a provided LabVIEW software that you can see on the screen. However, we did not want to slow down our computer engineers as they needed a lot of data to train their model. So we are using a power and energy logger to collect the raw power data. But the evaluation board definitely gave us experience and knowledge of using that powerful chip so we can develop our own system in the spring to meet the anticipated best outcome for the summit. So after collecting the power data, we are able to teach the model.
In order to teach the model, we first need to be able to define the structure of said model. Using the high-level diagram that we discussed previously, you can see that machine learning is simply a mapping between the input data, the power data, and the output, the fault modes. However, to be able to get a more intuitive understanding of machine learning, we can represent this high-level diagram using nodes, or more specifically, layers of nodes. As such, we can represent the input layer as simply a set of nodes representing the active, reactive, and apparent power. Similarly, with the output layer, we can represent that as a set of two nodes representing the normal and faulty operation modes. To be able to convert the input layer into the outputs, from the power signature to the fault modes, we need to do specific mathematical operations known as hidden layers. Hidden layers can implement operations such as addition, convolution, or some other higher level mathematical operation in order to convert the inputs to the outputs. However, to allow the flow from the input layer to the output layer, we need to utilize specific connections between the layers. These are known as the model weights. Model weights allow us to assign a certain level of importance to a specific output to a specific input to compute a certain output. This nodal analysis of machine learning is what is called a neural network. Neural network is one specific implementation of a machine learning algorithm. For our specific application, we needed to use a specialization of a neural network called a recurrent neural network. To be able to train a recurrent neural network, or to be able to train an ML model in general, there's a specific iterative process that must be followed. This process starts with feeding one instance of data to the model with a known classification. In other words, we know if it's either faulty or under normal operation. We then, using the previous model structure, produce a prediction, and then adjust the model weights, those connections between the layers, based on the relative correctness of our prediction. We then repeat this process for a set number of iterations until we have a set of model weights that are optimized for a specific application. In order to implement both these aspects of machine learning, we need to utilize what is called TensorFlow. TensorFlow is a high-level library developed by Google that allows us to not only describe the model structure, but to also facilitate the training process. Using TensorFlow, we were able to create a trained model that is capable of realizing our third major task of making predictions. Currently, we are not able to, our ML model is not able to understand the higher order relationships within the power data. However, consider this. At the beginning of this project, our team had no prerequisite experience of AC power analysis, machine learning, or any other core aspect to this project, yet we are still able to collect data, teach the model, and make predictions. In order to continue this momentum into the spring and achieve our anticipated best outcome, we will deploy our trained model on a system that can not only collect power data, but also make fault predictions in real time. This system is known as our inference system.
So, as Dan had mentioned, the future of our project lies with implementing the inference or prediction system within our final product. Simply put, we want the user to be able to simply plug their appliance into our system, and we collect and process the power signature data, and then output a response to let the user know whether the appliance is in a faulty or optimal mode. First step in this process is to find a way to store the machine learning training model within the system. For that, we're using a Raspberry Pi due to the processing power, the serial communication, and also the onboard Wi-Fi capabilities. You could think of the Raspberry Pi as sort of the brains of the operation, while the brawn would be the power monitoring chip, the ADE7880. So this is going to be housed on its own custom PCB, which essentially is going to be a condensed version of the evaluation board that we had worked with previously. It'll have the same functionality, so it'll be able to collect current and voltage data and then transform those into power signatures. From there, the Raspberry Pi is going to pull those over and then run it through the training model to create an inference or a prediction. The prediction is then going to be sent out to a set of LEDs, where each LED is going to represent a different fault mode, or if it's in an optimal state. If it is in a faulty state, we're going to have an email alert sent to the user just to notify them for this information. So if we think about this in broader terms, imagine instead of a fan, we had maybe an oven, or an MRI machine, or even your own car. The fact is that the technology we're working with has implications that expand far larger than just rudimentary appliances and can really have some beneficial effects across industries. With that being said, we'd just like to thank the following people for their continual support on our project. Thank you.